Welcome back to ECE 442-542. By way of announcement, homework number 7 is due on a Saturday, which is a little bit different than what our normal schedule has been, but that's on the 29th. Homework number 8 will be extra credit, and that will be due during finals week. And that's yet to be posted. Your project, if you're in 542, that's due the last day of class. And teacher course evaluations are also due on the last day of class. The final exam is scheduled for Thursday in this classroom from 1 to 3 p.m. And we may have a final exam review session. Stay tuned for that. Today what I want to do is go over PID controllers. We've been talking about proportional, we've been talking about PI. Let's add the derivative term, and I want to essentially quickly go through the derivation to show where the structure or how the structure arises. We'll actually end up with 2 fixed poles and 2 zeros that we can manipulate if we now say, oh, I want to introduce a PID controller, and we'll work through some examples. Where we are going after that is to look at a generic controller design, and by that I mean we may have unlimited options for where we place our poles and zeros. Now I told you you cannot cancel poles and zeros outside the unit circle or even on the unit circle, but we may want to place poles and zeros outside the unit circle. They just can't be placed to cancel anything outside the unit circle. But putting poles and zeros, we may want to, if we have an unstable system, it may require us to place a pole outside the unit circle to eventually stabilize the system. That's what I mean by generic controller design, and that's why it's important that we try to understand these root locus rules so that we have some way of guiding our decision process into where we put these poles and zeros. And we will finish the semester talking about state space controller design, and how far we get into that is up to debate or yet to be determined, but we'll get into state space control design, which now will be our final topic of the semester. We don't have that many more visits in terms of times that we're together. Here's our structure that we're working with now. It hasn't changed. We have our plant, and in the forward path we have our controller, which in this case it's a PID controller. And if that's the case, let's just look at what that means if it's an analog PID controller. Here's where it maybe has more intuitive appeal. If we now look at the proportional piece, that's just a gain. We look at the integral piece, that's now a division by S. That's what 1 over S as an operator does in the frequency domain. That really represents an integration in the time domain. And differentiation in the continuous time setting is in the frequency domain consistent with the multiplication by S. So we have a PID, and if we have those 3 terms, then we have a PID controller. And you can see with a PID controller, we actually have the ability to adjust 3 different parameters. And you could view each of those gains as an adjustable knob. The proportional knob, the integral knob, and the derivative knob. And the idea is you want to be able to adjust those properly to achieve the desired behavior that you want. And what we want to talk about now is actually how can we translate those 3 adjustable values in the analog setting into 3 adjustable parameters in the digital or discrete time structure. And what it will end up being is we will have the opportunity to place 2 zeros anywhere we want in the complex z-plane. We'll have forced on us a location of a pole at z equal 1. That's to give us our steady state accuracy. We'll have another pole right at the origin Those two poles are fixed in the PID control structure. And then once we've located those zeros, then we will have a gain adjustment. And that gain adjustment now is what we've been dealing with all since we started controller design, is what point on the root locus do we want our closed loop to scroll through how to connect the continuous time, the PID control structure, into this discrete time structure. First, we can, so you might see a PID controller written in many different ways. The first way is very clear, the P, the I, the D. The next line just factors out a common gain from all of those terms. And then the third line simply absorbs that ratio of gains into one variable, a T sub I variable, which let me go ahead and scroll down to show you what those are typically referred to. We have K, which is our proportional gain. That's just the K sub P value, and that's out front of our controller's parameterization. We have T sub I, which is integral time, and that makes sense. If you look in the expression, we have 1 over T sub I S. And what's S? S is a frequency. We're multiplying it by a variable T, and we want it to be dimensionless. So now we have Ts to being dimensionless, we need T to be a time, since S is something per time. It's a frequency. So T sub I is an integral time, but that's really just another way of thinking about K sub P over K sub I. So you could, if you had these three knobs, you could have a proportional gain knob, you could have an integral time knob, and you could have a derivative time knob, in lieu of having a K sub P, a K sub I, and a K sub D. It's the same, it's not the same knob, but it's the same idea. Yes? So now what you're wanting to do is K sub P would be probably dimensionless, and now K sub I, if you looked up here, K sub I would be having the same units as S. K sub I is like a frequency. And that makes sense on down in the expression for T sub I and T sub D. So everything should be consistent in terms of understanding. But what you want to take away from this is just, we still have three adjustable parameters, a K, a T sub I, and a T sub D. What we want to do now is connect or derive this expression. This is now an expression, a difference equation. It's relating the error, that's the input to our controller, to the input to the system U, which is the output of our controller. And if you look at this, what you can see is we do have memory. There's our integral piece. That's the input one sample period delayed. Then we essentially have three terms involving our error signal. We have the error signal at the present time, e to the n. We have our error signal one sample period in the past, e of n minus 1, and the error signal two time periods in the past, e of n minus 2. And what we want to do is see if we can chase down where this formula comes from in connecting the analog PID controller to the digital. And I may not give you enough time to copy all of those down, but you obviously have these notes available to you after the fact. So what I want to do now is connect the C of S with the C of Z. I just gave you our goal. That was C of Z, or the time domain version of it. Now let's see how we can go from a C of S, which is our analog PID controller, And again, it's written in terms of the proportional gain, the integral time, and the derivative time. The second or the middle row now, all we're doing is we're factoring out an s in the denominator of every term. That's our first step. In going from the generic PID structure to this middle line in this derivation. So all we're doing is manipulating the expression by factoring out an s in the denominator, which then in the 1, that gives us an s. The 1 over t sub is, we're removing the s and putting it out front, and then we had a t sub ds. We divide that by s, and that basically then gives us an s squared in the t sub d s squared term. Then we can multiply both sides through by s, and now we have su on the left-hand side, and we have this operation on our air signal in the frequency domain, where we now have a derivative, we have a constant, and we have a second derivative of our air signal. But on the left, what do we have? In the time domain, what is that equivalent to? On the left, what is SU equivalent to in the time domain? So S is an operator. If we had 1 over S, what's that operator? 1 over S is integrating. So now multiplying by S is differentiating. So on the left-hand side, we have the derivative of our input is equal to the derivative, a scaled version of our derivative of the air, a scaled version of the air itself, and a scaled version of the second derivative of our air. And we want to use this to now see if that will allow us to come up with this expression in the time domain. That's our goal. What I just said is now echoed in the time domain in this next row of the derivation. We have the derivative of our input of the system, which is the output of our controller, is now going to equal a scaled version of the derivative of our air, a scaled version plus a scaled version of the air, plus a scaled version of the second derivative of our air. And what we can do now, we want to go continuous to discrete. And we'll do that by using the backward Euler, just to show the connection of how we could find that difference equation that gave us an expression for a PID controller for a discrete time system. A derivative, the u prime on the left with the backward Euler says, oh, take the present value of the input, subtract the input 1 sample period before, and divide by t. That's an approximation of the derivative. And we're just going to continue to use that approximation of the derivative throughout. And these highlights will make sense in a minute. But you can see that I'm highlighting these errors at different time indexes. And so yellow, I've now circled all of the errors at the present time, E of n. But I hope it's clear that on the right-hand side, we have k with a square bracket. Then we need to approximate the air, the derivative of the air, again using the backward Euler approach. And so we have E of n minus 1 over t. If we take E of t and take that into the discrete setting, that's just E of n. That's E at the present time. We're not explicitly showing the sample period in the argument of each of these expressions. We're just saying E of n, that means E of n sample periods. And then we have plus t sub d, and we had the second derivative of our air signal. Well, let's now at least start by finding approximation of that second derivative by writing it in terms of first derivatives. Meaning, we take e prime of n minus e prime of n minus 1 divided by t. And that now gets us one derivative less than e double prime in the discrete time setting. And you can see what's going to happen. We need to eliminate, because we don't know what that means, to differentiate a discrete time variable at any sample period. That really doesn't make sense. So inside that curly bracketed expression, we're going to expand that out into a couple more derivatives, approximations of derivatives. We approximate e prime of n. So again, all I'm doing right now is replacing what's in the curly brackets. Now that's shown in the red curly brackets. The top left-hand term is just an approximation of e prime of n. The rightmost term on the fraction inside the red curly brackets is just the derivative approximation of e prime of n minus 1. And now, if you put the red curly brackets in place of the blue curly brackets, that's our entire expression. Is that clear what I'm wanting to do? I now have everything in terms of u of n minus 1, e of n minus 1, and e of n minus 2. And I just need to basically do the algebra to clean that up. But to do that algebra, what I've actually done is I've tried to highlight the common error terms at a particular time index, meaning the yellow highlights represent the pieces of the right-hand side formula that involve e at the present time, the error at the present time. The light blue is keeping track of those terms that is the error signal one sample period before now. And the green highlight, I only have one of those, is the error at time n minus 2. Meaning, remember what we were trying to find? We were trying to find this equation. U of n is equal to something. And we have a u of n and we have a u of n minus 1. What we want to do now is make that happen with this. And we can quickly find u of n on the left by multiplying both sides through by capital T. And that will now eliminate some of these t's in the denominator. And the red bracketed term, it only eliminates the very bottom t. We still have some t's underneath some e's in the red bracketed term. And the red bracketed term, don't forget, is scaled by t sub d inside the square brackets, which outside the square brackets, every term is scaled by capital K. Meaning, if you follow all of this algebra around, then you will find that the yellow terms, look at how many terms we had in the yellow. We should have 3 coefficients that help produce the coefficient that could be all scaling e of n. We have 3 different pieces. We have a k piece, we have a k over t sub I piece, and we have a t sub d over t piece that all scale little e of n. Is that true? Well, if we go down to this next line that I've now underlined in yellow, yes, we do. I've kept the k still factored out, and we have a 1 plus a t over t sub I plus a t sub d over t. And maybe instead of keeping track of all those t's, t sub I, t sub d's, we'll just absorb all of those into one constant and say that's a new parameter, alpha 0. Similarly with E, for whatever reason I changed my indexing. These are L's, but we have U of L, that's the same as U of N. L's are easier for me to write maybe than N's. But I now have U of L is equal to U of L minus 1. That right there tells you have a pure integration. Then you have the rest being determined by delayed versions of your error signal, E, and the error at the present time. But if we simply collapse all of those coefficients or parameters that are scaling the E, the L minus 1, and the E, the L minus 2 into an alpha 0, an alpha 1, that's with 1 delay, and the alpha sub 2 is with 2 delays, then we can simplify that expression into something more like this, if we take it into the transform. So I've now not only consolidated or removed all of those coefficients, but at the same time, I've taken it into the frequency domain. Meaning U of L, little u of L, when I Z transform, becomes just a shift. I just capitalize it. It's now capital U of Z. Little u of L minus 1, that's just a delayed version, and we know what a 1 sample period delay looks like in the transform. That's Z to the minus 1. K comes right through when we go from time domain to frequency domain. We haven't done anything with our K. That's not a function of Z. But we now have alpha 0 little e of L. When Z transformed, that just becomes capital E of Z scaled by alpha sub 0. Likewise and here my alpha 1, I'm going ahead and including that negative coefficient inside alpha 1 so that all of my coefficients in the bottom row that's on the screen right now have positive coefficients. I have alpha 0, alpha 1, and alpha 2. Alpha 1 is scaling the 1 sample period delayed version of our error, and now you can see what else I can do. The error is common to all three of those terms. I can pull it out on the right, and I can move my U terms to the left so that I now have 1 minus Z to the minus 1. That's operation scaling capital U of Z. What am I trying to do? I'm trying to actually find another way of writing this PID controller in the discrete time setting so that I can play with it more directly. If I now find my controller's transfer function in the discrete time setting, that's U over E, then C of Z is just the numerator over 1 minus Z to the minus 1, which I can clean up or write in terms of advanced operators on Z by multiplying by 1, where 1 is Z squared over Z squared. And in so doing, I now have my controller for a PID controller in discrete time written in terms of positive powers of Z. I can now say that that's K times alpha sub 0 Z squared plus alpha 1 Z plus alpha sub 2 all over Z squared minus Z, but that's now Z times Z minus 1. And I hope that you can see that now in this PID controller structure in the discrete time setting or in the frequency domain, I don't have any freedom to move the poles or the pole factors. Where are my poles in this PID controller? I have 1 at the origin. Z equal to 0 will cause the denominator to vanish, and Z equal to 1. So if I say I want you to design a PID controller for this system, immediately you can put a pole at 1 and a pole at the origin, and now you have total freedom to locate 2 zeros. And then you can crank up the gain, K bar, to give you or put you on the root locus where you want to live. But you want to pick the beta 1 and the beta 2, your 2 zero locations, such that your root locus is in the shape or pattern that you hope it to be. This is now our PID controller. in the frequency domain. Or if you wanted to think about that in terms of your shakers, when we're designing controllers, now if somebody says if you're designing a controller, you can now have a zero shaker and a pole shaker, and you want to now sprinkle poles and zeros on the complex plane to give you the flexibility that you want to achieve the root locus that will give you the dominant poles that you want. Which means then in a PID controller, this is what you have to work with. You have a fixed pole at the origin, you have a fixed pole at 1, but now these zeros can be adjustable and they can be complex conjugate. Those zeros don't have to be real. They could be off the real axis, and that might be of advantage to you. What you have the ability to do is then locate those zeros. Now, what is not shown in this Z-plane is where your poles of your original plant are. That will influence where you locate beta 1 and beta 2. But you'll plot beta 1 and beta 2, and those betas, if you wanted to maybe simplify your design, those might be selected to cancel certain poles that are inside your unit circle. You could do that, and that might simplify your analysis. Here's the design process with a PID controller. It introduces 2 fixed poles. One pole is at 1, which gives you the good steady state accuracy that you want. If you want better steady state accuracy, then you're putting poles at z equal 1. But what's the trade-off? The more poles you put at z equal 1, the more challenging controlling your system is going to be. There's this trade-off between transient behavior and steady state accuracy. You may want your system to lock on to a constant input reference. Oh, well then I want to put a pole at 1. Well, that might make your job of controlling the system a little bit more challenging, or you may have to now sacrifice a little bit in the transient behavior of your system. PID controller, then we have 2 fixed poles. One's at z equal 1, and the other allows us to have a causal controller. What's that mean? Do you remember what a causal controller corresponds to physically or in a pole zero or in a transfer function setting? What's required for it to be causal? Or what can you not have happen in a controller if you want your controller to be causal? And causal just means that it can't anticipate an action before it receives information. So it can't do that before you hit it. That would be anti-causal. The controller, you want to respond to an action after that action has happened. So it has to respond once it's measured an error. It can't respond before it's even measured an error signal, which really means that you want your numerator polynomial to be of the same order or less than the order of the denominator. And we have 2 finite zeros in this PID controller. We have to have at least 2 poles. And that's where we have this pole at z equals 0, and that's a fast pole that we have access to. Then the designer, that's you, the designer can select 2 zero locations, and those zeros could be either real, or if you want them to be complex, they have to be in conjugate pairs. So they have to be in the same place in the upper half plane as they are in the lower half plane. Now we can start playing with some design. Here's a system. Let's say you're given this g of z, and you want to control it. So there's the boundaries of my unit circle. And where's my pole of the system? It's right there at 3/4 in the positive half of the z-plane. That's the value of z that causes that denominator to vanish. Can you stabilize this system with a constant controller, with a proportional controller? Can you stabilize this closed, if this plant is in a closed loop setting with a gain, an adjustable gain k, can you stabilize this system? Yes, the root locus for a proportional controller is just all to the left. You obviously have a limit. You can't crank up the gain too much. You would want to keep the gain less than what the gain would be to drive you outside of z equal -1. Is that clear? If you had a proportional controller, though, you're going to have a offset between your reference input and the output. And maybe you don't want that. Maybe you want to have 0 output to a constant input. I put in 4, I want my output to go to 4. I put in 3, I want it to go to 3. I put in 12, it'll go to 12. How's that going to happen? How do I guarantee that I have 0 error due to a constant input? What was the answer? I want a z-1 in the denominator, or I want to put a pole of my controller at z equal 1. And one way to do that, without even getting too complicated, is to just do a PI controller. A PI controller, and what would be an easy way to guarantee steady state errors of 0 and not have too complicated of a pole 0 pattern? Where do I put the 0? At 0. What if I simplify it even more and put the 0 right there? If I put the 0 right on top, what's my root locus look like? My root locus now looks like this. That's pretty easy, isn't it? That's almost a trivial design. So now my PI controller would be K z minus 3/4 over z minus 1. And how would you pick K? Or what are you wanting K to achieve? Or what does K do for you? K now moves you along that red line, correct? And that red line shows you all the possible, all the potential closed loop poles for this choice of controller and that plant with this proportional control, or this K adjustable. I've already picked a 0. My 0 factor I selected to simplify my analysis, and it's canceling that plant pole at 3/4. I could now adjust K to put me somewhere between 1 and -1. And I probably don't want to be in the left half plane because that makes my system oscillate back and forth with my dominant pole. Meaning I may crank up the gain K to put me maybe there. Do you see how you would use the magnitude condition to find the K to get you to that triangle? And then your design would be finished. You would say, oh, I want to have my triangle at 1/2 to give me a particular speed of response. What's the K required to do that? I would use the magnitude condition to make that happen. In this case, then, K is selected for the speed of response. Now, you guys are going to be well-compensated engineers when you finish. That means you have to have some expertise or some experience. Now, what could possibly go wrong with this design? Or what are we assuming in this design? Now you want to be, as an engineer, you need to be starting to play devil's advocate on yourself, on your own design. And you're saying, okay, this looks kind of trivial. What could possibly come back and bite me? What could cause me problems? What do you maybe, hopefully, you can easily produce a controller that has that transfer function, because that's on you, right? That's your Arduino, that's your computer. You can now create a difference equation based on those coefficients. What might you not have the ultimate control over in this problem? The sample period you can select. You have pretty good control over sample period, so that's already been selected for you, hasn't it? Because I didn't tell you anything, I just gave you a G of Z. So the sample period has already been determined, and that did what? Well, that put that pole of your plant at 3/4. But what if there was some uncertainty in your system and you modeled it this way, but your model is not quite what the actual plant is? Is that making sense? The true system might be first order, but it may be a G hat of Z that has a pole that's not right at 3/4. Oh, great. What's going to happen? Well, we can look at some possibilities. So here, what I want you to think about, this is your expertise, is what about the fact that maybe we don't have an accurate model of the true system? What about uncertainty in the actual pole location? Meaning, now what do? You're trying to explain this to your boss, and she goes, I don't understand. What do you mean by uncertainty in your plant? You go, well, I modeled my plant as 1 over Z minus 3/4. But the plant might actually have a pole. Let me see, where did I put it to begin with? Maybe my pole is actually at 0.7 in the actual system. It's not at 0.75. There's the plant, the true system. And you modeled it as a pole at 0.75. What did your controller do based on this? Well, now your controller, can I put the controller poles and zeros in red just to distinguish them? You have a PI controller that you put a pole at 1, and where did you put your 0? At 0.75. This is what you're going to have in the actual system. What's the root locus of this look like? Is it much different? That pole is going to approach that 0 at 0.75. And what happens to the pole of your true plant? As you crank up the gain K, it's going to march off there. So the gain that you've picked to produce this speed of response, now how many branches of the root locus do you have? 2. How many closed loop poles do you have? 2. You had 2 before. 1 just got ideally canceled. But now if we crank up the gain to what we had before, this pole is going to be right there. It's almost canceled by the 0 of our controller, and this one should be close to where we put it, which was 1/2 before. meaning the system behavior should be about the same, even though there's some difference between your model, which had a pole at 3/4, and the true system, which had a pole at 0.7. Meaning on the exam, I could say, design a controller, PI controller for this plant. And then I would say, oh, my bad. Now analyze the closed loop behavior with a true system with a pole at 0.7. And then you would draw this. And you would say, this is what's going to happen. What's the other possibility? So this is a z-plane possibility that you've shown to your boss. And then you say, well, it's just as likely, maybe, I modeled it as being at 0.75. Maybe it's not at 0.7. Maybe it's at 0.8, the true pole. What's that do for us? Now our pole, true system, is at 0.8. We put a pole at z equal 1, and where was our 0? 0.75. Now what's this root locus look like? This is why we played with root locus. You should see this right away. This is 2 poles and a 0 with 2 real poles to the right and a 0 to the left. This one I just kept hitting you with before the exam, right? Stop, stop. And you know what this looks like. You have these 2 poles coming together. They break away at the geometric mean defined by the 0 and the pole location. You can calculate that, but it's somewhere here. Then they form a circle, and that radius is not very big. And what happens? One pole goes here, and one pole goes there. And what's the possibility now? You've picked a gain k based on your model at 0.75. Now, you're probably going to have the gain put you with a pole there and another pole right there in the closed loop. Meaning one of those 2 closed loop poles is almost being canceled by the 0. You've now zipped around the 0, and the other one is at the 1/2 location or close from your original design. Questions on that? So in the first case, your pole, the true pole, was at 0.7. In the second case, or possibility, the true pole of your system was at z equal 0.8. Do you see how your tools of root locus sketching allow you to think through these options? And why did these options arise? It's maybe because there was some inaccuracy between your model and the true system. And your techniques, controller techniques, actually give you a pretty robust design that results. They look just about the same, even though maybe the root locus diagrams are a little bit different. But eventually they start giving you the same behavior. All right, that was a PI controller. Let's look at another system. Suppose now that you're given a system that is 1 over z minus 2. What can you do with this guy? Is it stable, open loop? No. You have a pole at 2. So you have to do something. If you implemented a proportional controller what do you know might happen with respect to steady state accuracy? If I put in a 4, will you reach 4 with a proportional gain? Can you see the root locus of this with a proportional controller? It's exactly like the root locus in the last example, except now we're starting at 2. We would now need to have a minimum value of gain k to get a stable. That would be determined by the k, the magnitude condition, solving k when z is equal to 1. The maximum k would be when z is equal to minus 1. We have some region of k that we can stabilize our system with. But we would not have 0 steady state error due to a constant. We would have some offset. I put in a 4, and maybe it goes to 2.76. And maybe I don't want that. Maybe I want it to lock on. And how do I get it to lock on? How do I get 0 error due to a constant input? I make my controller plant combination be of type 1, which means I want to force a pole factor in that product to be at z equal 1, or to have a pole at z equal to 1. If that's the case, let's now look at what we can do with a PI controller. There's my uncompensated plant. I now have a PI controller which has introduced a pole at 1. Where do I put my 0? Do you see why I kept hitting you with this structure? I didn't bring in my steel-toed shoes as I had suggested last time. And I noticed a lot of the front row didn't show up because of it, or they are sitting further back. But where do I put my 0 of my PI controller? Do I put it between 1 and 2? No, that's not a smart choice, is it? Or a wise choice, I should say. I probably want to put it to the left of z equal 1. And if I do, then you know exactly what the root locus looks like. And that might influence where you put beta, or where you put that 0. If you put it here, for some reason it didn't like that. So let me try it again. We put it here. These two go together. We have the geometric mean again, determining our radius. And what are we wanting to do? We're probably wanting to crank up the gain such that we get inside that unit circle. That's what we want to do for this PID controller. So now let's see how we can maybe design this more than just sort of guess. You could guess a beta and then draw it and pick a K and work with that. But let's see if we can actually do a design a little bit more analytically. So now let's select beta to produce closed loop poles where we want them to be. Select beta to produce a desired root locus path or shape, however you want to refer to the, and K will then be selected or is used to fix the dominant closed loop poles. Now, suppose one has already in mind a particular set of dominant poles. Suppose one wants dominant poles Z delta to be at 0.9 plus and minus J 0.1. That they've determined this will give me the dynamic behavior that I want, the transient behavior that I want, and I'm assured of having the steady state accuracy that I need because I've already forced a PI controller structure on this problem. Is it possible to place my dominant poles there at 0.9 plus and minus J 0.1? Is it possible to get my root locus to pass through those triangles? I want to now see if I can answer that question. It's not the way I've sketched the root locus, but maybe if I am able to more analytically determine beta, maybe I can figure out how to make the root locus go through those triangles. But the question now that we're looking at is it possible with PI control to make this happen? That being the case, let's draw this in a little bit more magnified way. We had our open loop pole at 2. We had a PI pole at 1. And now what we want is we want this and obviously we have its twin or cousin and the conjugate location, 0.9 minus J 0.1. We want to now see, is it possible to put a 0 in here at beta? This is now located at beta in order to have our root locus go through those triangles. If those triangles are not on our root locus, what do we know has to happen at those triangle locations? Do you remember? What determines the shape or the location of our closed loop poles? They have to be satisfying that 1 plus kg bar of z equal to 0, which means that kg bar of z has to have an angle of what? Minus 180, which says that the angles, the algebraic sum of the angles of this pole 0 pattern need to be such that they combine to get an angle of minus 180 at that triangle location. If that's the case, then we know that for that choice of beta, the root locus does go through that triangle. If we can pick beta to make the angle due to those poles and 0 equal minus 180 for that choice of beta, then we know our root locus goes through those triangles. That's the plan. Meaning, what I'm trying to do is I want to now use the phase angle condition to find beta. Now I've already picked z sub delta, and I know I have a pole at 2 and I have a pole at 1. The only unknown right now is beta, meaning I can either analytically or with my protractor, I can measure that angle from 2 to 0.9 plus j 0.1. I can compute that analytically, or I could measure it with my protractor. I can also measure this angle. So let me call this angle the pole P2, the angle theta due to pole 2 since it's at 2, And let me call this angle the angle. So now that's the angle that if I'm standing at 1, what do I need to turn in order to see that triangle? That's the angle that I want to rotate through. Let me call that theta p sub 1. But you can see that I've sort of pre-selected that triangle location to make some of these calculations somewhat straightforward. How far over do I need to go horizontally to move from 1 to the triangle? Now I wish I had my steel-toed shoes. If you didn't hear that, somebody commented that we needed to step 3 units to the left, forcing me to want to kick. My instant response was to kick, but I don't have a ball, so I'm not going to punt or kick anything. I wouldn't kick a person. Not tonight. So let's try that again. How far would I have to move from z equal 1 over and be right underneath the triangle? The triangle is located at 0.9 plus j.1. I need to move from 1 to 0.9. That's not hard to calculate, I hope. So I'm moving, and it's not 3, it's 0.1. Then how high up do I need to look? What's my vertical displacement? To go from the real line to 0.1 is 0.1. So now the acute angle is 0.1 plus a vertical of 0.1. It's at 45 degrees. My obtuse angle, or the supplementary angle, is now 180 minus 45, or theta p1 was easy. That's 135 degrees. Is that clear? This now, by the choice. Now, in reality, you probably don't want to be designing, making your angles nice. You want to do it to meet your design specifications. But here, I want you to understand where these angles are coming from and get the process down. That's the important thing, and making those triangles at 0.9 plus j.1 helps do that. Are we clear with where theta p1 came from? And we also need to worry about this angle, which I'm getting kind of messy. I thought I magnified that up, but I'll call that theta sub z. And I don't know what that is, but that's going to be my unknown variable that I'm solving for. From my phase angle condition, is it clear from the phase angle condition that I need theta sub z minus the angles of my poles I need that algebraic sum of all my poles and zeros to equal minus 180. And what's theta p sub 2? That's not as easy, but I can find the acute angle pretty easily, and I can take that and subtract it from minus 180 to actually get my theta sub p sub 2. Meaning, what's the acute angle between 2 and that triangle? How high up do I need to look? What's my vertical? Not my vertical jump. That's not very high anymore. That's the key word. But this is now the inverse tangent of what? Vertical. What's your vertical? 0.1. That's about my vertical now. It's 0.1. What's my horizontal? Now I need to move from, what is this for? Theta sub p. This is the pole at 2. I now am moving a distance of 1.1. Is it clear where that came from? That's usually easier to do than trying to find theta p2 directly. And your calculator a lot of times likes to just work with angles between plus and minus 90. So this makes it easy. Which, if you do this isn't a very big angle. This is 5.194 degrees. So that now we subtract that from 180. the angle contributed by that pole at 2 is now 174.8 degrees. And we know theta P1, this was 135 degrees. The only unknown which we can now solve for is theta sub z. Theta sub z is now, or maybe I won't say equal, let me just keep it the way it was. It's minus 135 plus 180 minus 5.194 equal minus 180. So that this is actually a minus 180. That cancels that minus. Question? So how did I find theta P1? I was walking around. I was trying to illustrate this. I'm now at z equal 1. And I want to know what's the angle that I have to turn. So I'm facing in the right positive direction on the horizontal, and I want to turn the angle necessary to get me to look at that triangle. Well, to do that, I focused on the acute angle, which is over 0.1 from 1, and it's up 0.1 from the real line. So I now have a 45-degree small angle to get me from z equal 1 to that triangle, and so I need the bigger angle, which is 180 minus that 45. So that's where that 135 came from. Is that clear? Beta, or the zeros angle, I don't yet know. But I just calculated theta p sub 2, that's this guy. And I actually, by keeping it separated as 180 minus 5.194, that simplified my algebra a little bit. So that theta sub z, the angle of my zero, is now going to be 135 degrees. And I had a plus 5.1 on the left. I'm moving it to the other side. It's now minus 5.194. Or I basically have 130 degrees. But if I keep track of the significant digits, let's say that that's now 129.8. What am I trying to do? I'm trying to find the location of my zero. I've now found the angle that that zero makes with the triangle. In a picture, I now have that triangle right here. And where's my zero? And this is 0.9, and this is now 1. I'm a little bit exaggerating to give myself some space. But where is my zero located relative to that triangle if the angle of that zero is 130 degrees? Am I to the right of the triangle, or am I to the left? So if I was right under the triangle at 0.9, my angle would be 90 degrees. If I move a little bit more to the right, my angle is getting larger, which is closer to 130 than if I move to the left. Is that clear? So my zero is actually needing to be over here relative to that triangle, so that my angle here, this is my theta sub z, that's my 129.8 degrees. What do I know? Well, I know that this distance is 0.1, and I can, if you wanted to, I could work with this angle, since I like working with angles less than 90, and these right triangles are easier to deal with. So if I call this sort of theta sub z bar, the supplementary angle to theta sub z, I can now compute what this horizontal distance is between 0.9 and the beta location. This is at beta, and I'm now saying that I want to know what is this distance x bar that I have to move to the right so much from 0.9 to get me my beta. And I can find that x bar from trig. Once I have x bar, I can use 0.9 and x bar to find beta. Is that clear? Or I now can say that I have 0.9 plus x bar is beta. And what's theta sub z bar? That's just 180 minus my theta sub z, which that's 180 minus 130 roughly, so it should be close to 50 degrees, and it's 50.194 if I keep my significant digits. And now what do I know? Well, I know the tangent of that angle is equal to the vertical over the horizontal by definition of the tangent. And the only unknown in that expression is x bar, and now I can find x bar. X bar is 0.1 divided by the tangent. And that now gives me 0.0833. Or, again, if I wanted to try to sketch this so that I remind myself what I have, here's 0.9. Here was beta. I now know this distance. That's supposed to be a 0. Or beta is now 0.9 plus x bar, or this is 0.9833. So what? What do I now know in this process? I'm designing a PI controller. I'm trying to remind myself what in the world I'm doing. I kind of got lost. I'm designing a PI controller. What does that immediately say? I now have a pull factor, z minus 1. What did I just compute? The 0 factor. Do I have any more flexibility? I haven't yet picked K, have I, in this PI controller? How do I find K? Or from this, can I now sketch a root locus? Probably should have made this bigger, but this is now at 2. I had a pole there, and I have another, and I have a 0 right there, right? At 0.9833. It's very close to z equal 1. But now I can compute the breakaway, and we know that the breakaway happens between 1 and 2, but it's very small because it has to now pass through the triangle, which is at 0.9